So today's lesson, 9.2, intersection of planes, and in this diagram here, I'm showing you three different possibilities for the intersection of two planes. We're going to start with two planes, then we're going to also look at three planes. So one possibility is that, well, they intersect, but notice when they intersect, they don't intersect in a point, they intersect in a line. So that's an infinite number of points. Another possibility is that you have two parallel planes, in which case 0 points of intersection. And our last case is where we have two coincident planes, so the exact same plane, one lying perfectly on top of the other, and therefore infinite number of solutions. So what we can do is, if we have our planes, we can analyze their normals. So plane 1 has a normal n1, and plane 2 has a normal n2. Now we know if n1 is some scalar multiple of n2, then the planes are either coincident or parallel but not coincident. So that's either going to be case 2 or case 3. However, if one is not a scalar multiple of the other, then they're going to intersect in a line. Let's look at some examples. We're going to go to the next page, and we're going to look at the first example here. So this example says, determine the solution to the following system of equations. So we have two planes. Let's call the first one just pi 1, and the second one pi 2. All right, now from that I can pick out their normals, because remember their normals are just the coefficient of those terms. So n1 would have normal 2 for the coefficient of x, coefficient of y is -1, and our coefficient of z is 3. So there's the normal for the first plane. The second plane would have the following normal. So x has a coefficient of 1, there is no y, so that's 0. And z has a coefficient of -3. So just looking at their normals, we can see that n1 can definitely not be written as some scalar multiple of n2. It's not going to work out. So it means the planes are not parallel, and they're also not coincident either. So they're going to intersect, and they're going to intersect in a line. So what we can do, we can start by looking at pi 2. So let's look at the equation for pi 2. But I'm going to say z is going to equal s, some value s. Now when I do that, the equation for pi 2 becomes x minus 3s equals 1. And we can rearrange to solve for x. So x is going to equal 1 plus 3s. All right, now I can go and look at pi 2. Sorry, pi 1. I just looked at pi 2. And pi 1 has the equation 2x, but I'm going to substitute what I have here for x. So 2 times 1 plus 3s. Then minus y, don't know what y is, that's what we're going to solve for, and plus 3z, where I'm saying z is s. That'll equal -2. So we can rearrange this a bit, so expand and simplify. So expand the brackets, we are going to get 2 plus 6s minus y plus 3s equals -2. Okay, we can solve for y. So y will equal 9s plus 4. Therefore, I have my parametric equations for that line of intersection. So here's our parametric equations. I'll write them out again. X is 1 plus 3s. Y is 4 plus 9s. Just rearrange the terms. And z is just s. And if you want to take that a step forward because you love vector equations of a line, you can do that as well. You can say the line with the vector equation is just 1, 4, 0. 1, 4. I'm having trouble with my pen today. 1, 4, 0 plus some scalar multiple s times 3, 9, 1. So there's the line of intersection for our two planes. All right, so our second example, it says determine an equation of a line that passes through the point P, 5, -2, and 3, and is parallel to the line of intersection of these two planes. Let's just draw it out. Okay, it sounds kind of complicated at first. So here we have one plane. Let's call it the orange plane. Here we have another plane. Call it the blue plane. Or just pi 1 and pi 2. It's probably easier. And they each have certain normals, right? N1 and N2, respectively. Now notice that line of intersection is going to be perpendicular to both those normals. That's a point we're going to use in a second here. And then we have some line somewhere else which is parallel to that line of intersection where this point exists on the line. And we need to find an equation for that line. Okay, there's two methods we can do here. Let's start with method 1. It's called method 1. Now method 1 uses what I just talked about. If the normal for plane 1 is perpendicular to that line of intersection, and the normal for plane 2 is perpendicular to that line of intersection, we can find a direction vector, M, for the line of intersection by taking the cross product of normal 1 and normal 2, because that'll give us something that's perpendicular to both. Alright, so the first normal then, we can pull out our coefficients from plane 1, so 1, 2, and -1. Cross our second normal, which is, we have no x term, so 0, 1, and 2. And we're going to apply our cross product to this. So that's going to give us, we'll have 4 plus 1, 0 minus 2. And if you need to, you can go back and review what the cross product is. And 1 minus 0. Or go watch the lesson on cross products. That's going to give us 5, -2, and 1. So there, we have a direction vector. Now that direction vector, since this line is parallel to that line, they have the same direction vector. Or we can use the same direction vector anyways. And since we know a point on the line we're looking for, there we go. The line we're looking for then, we can write a vector equation for, where we'll start with that point as our position vector, 5, -2, and 3, plus some scalar multiple, I'll call it S, I feel like S's today, times our direction vector, 5, -2, and 1. So there's method 1 to figure out the equation of that line. Alright, so now let's look at method 2. How can we get this with a different method? Now method 2 is very similar to the first question that we did. What we can do is first find that line of intersection. So if you like Z, I like Z. So let's say, okay, if Z equals T, I'll do something different from S. If Z equals T, then let's look at pi 2. So the second equation, we would have Y plus 2T equals 1. Okay, so then solving for Y, we just get Y equals 1 minus 2T. Then we can go look at pi 1, and we're going to find what x is. So the equation gives us x plus 2y, but we know y to be, we know y to be 1 minus 2t. And then minus z, which we stated was t, equals 6. Scroll down a bit. Alright, so now we can just expand and simplify, then solve for x. So x plus, so expand this bracket, so we get 2 minus 4t minus t equals 6. So x is going to equal 6 minus 2 is 4, and then plus 5t. Alright, so there's our parametric equations. We have x equals 4 plus 5t my pen doesn't work so well on the school computer. And y equals 1 minus 2t. And finally z equals t. Now from that we can pick out the direction vector, because again the direction vector for the line of intersection between the two planes is the same as the direction vector for the line we're looking for, because those lines are parallel. And our direction vector here will be our coefficients with t. So 5, -2, and 1. So r equals, our vector equation will be the point P on the line, which is 5, -2, and 3, plus t, and our direction vector, 5, -2, and 1. Alright, so now we're going to look at possible intersections with 3 planes. So first, we can have the planes like this, pi 1, pi 2, pi 3, and you'll see they intersect in one point. Or we can have them like this, almost like a book, where they all intersect along that line. We could have 2 of those planes being coincident, and then a third plane crossing it, intersecting in this line. Or we can just have all 3 planes coincident, like so, all lying on top of each other. Some inconsistent systems for 3 planes, which don't have all intersecting at the same point or line, would be if you have sort of this triangular shape. Right? So on this line, L1, right, you have pi 1 and pi 2 intersecting, but pi 3 doesn't, and so on. Right? You have this one where 2 planes are parallel. So right here along this line, you only get the intersection of pi 2 and pi 3. And on this line, you get the intersection of pi 1 and pi 3. Or you could just have all 3 planes parallel, or 2 of those planes could be coincident, parallel to a third. These don't work out too well. So let's look at an example. So this example here says determine the intersection of the 3 planes with these equations. So we need to figure out what x, y, and z are. Okay, I've run out of space on this page, and I knew I would, so I prepared this page. Alright, solving 3 equations for 3 unknowns. I taught you an easy way to do this yesterday, or at least not easy at first until you get practice with it, but an efficient and concise way of doing it. So I'm going to do that again, just so you can see how that works. And I'll set up the matrix. So first we'll have 1, -1, and 1. So I'm pulling out the coefficients for x, y, and z. So 1, -1, 1 equals -2. And then our second one, 2, -1, and -2 equals -9. And our third one, 3, 1, -1, and -2. Alright, so my first step is to get these two to be 0. The first row is not going to change. So let me just write the first row. 1, -1, 1, and -2. Now to make that 2 a 0, what I can do is I can multiply row 1 by -2, and then add row 2. If I do that, I'm going to end up with 0, 1, -4, and -5. And then to make that 3 a 0, I can multiply row 1 by -3. And then add row 3. So if I do that, I get 0, 4, -4, and 4. And then finally, I need to complete this triangle here. I want all those to be 0. I'm going to need that to be 0. So to do that, what I can do, remember I don't want to work with the first row, because if I work with the first row, that term will no longer be a 0 anymore, right? 1 times anything other than 0 plus 0 is not going to be 0 anymore. So I want to work with this row. So if I take that number and multiply it by -4, then I can add it to row 3. So let's do that. So for the last row, I'm going to multiply row 2 by -4, and then add that to row 3. So that gives me the following: 1, -1, 1, -2. So the first two rows just stay the same. 0, 1, -4, and -5. It's really hard to write today. And then we end up with 0, 0, 12, and 24. Now what we did with this last day was we took it, and you can easily do this, right? 12z equals 24. Divide both sides by 12, you get z equal to, well, 2. Right? And then you can substitute that into here and then continue on. But I'm going to show you another little trick you can do with matrices. So I'm going to continue my work up here. So I'm going to write equals. And what I'm going to do is just take row 3 and divide it by 12. So if I do that, so row 3 divided by 12, first two rows are going to stay the same. So 1, -1, 1, and -2, 0, 1, -4, -5, and then finally we'll get 0, 0, 1, and 2. So now look at that there. In this case, we have z equals 2. It's right there for us. Right? How easy is that? Now notice this whole line is 1s. That's great. Right? We can work with that. If not, we can change it just like I did right here to make it 1s, just by dividing that row by whatever you need to. Well, now what I can also do is I can work backwards to make this triangle also 0s. Wouldn't that be great? So let me show you how I'm going to do that. Step 1, I need to work with that second row. So how can I make this row 0? Well, I want to work with row 3. And so if I multiply row 3 by 4 and add row 2, it becomes 0. And that also doesn't change any of these numbers before it, because row 3 is 0, 0 to begin with. All right, so the second row, I'll do 4 times row 3 plus row 2. So if I do that, row 1 is still the same. 1 minus 1, 1 and minus 2. Row 2 becomes 0, 1, 0, 3. And row 3 is the same. 0, 0, 1, 2. So now look at that. Z equals 2, Y equals 3. Almost done. Right? So how can I make these two up here also 0? So we're going to continue with that. You know, this is like super exciting. So we're going to start by making this one 0. And to do that, again, let's look at row 3. If I multiply row 3 by negative 1, then this is negative 1, this is 1. And I can add them to make that 0. So let's take row 1 and multiply row 3 by negative 1, and then add row 1 back to it. So if I do that, you'll get 1, negative 1, 0, and then negative 4. And then rows 2 and 3 haven't changed at all. Finally, we want that to be 0. So to make that 0, I can take row 2 and just add them. Right? 1 plus negative 1 is 0. All right? So I'm going to take row 2 and add row 1. And that gives us, well, 0 plus 1 is 1. 1 plus negative 1, 0. 0 plus 0, 0. And then 3 plus negative 4 is negative 1. And rows 2 and 3 don't change. 0, 1, 0, and 3. 0, 0, 1, and 2. Therefore, these planes intersect in a point, and that point is x equals negative 1, y equals 3, and z equals 2. There's our point of intersection.